Hey guys, welcome back. As promised, to do a couple examples of L'Hopital's rule here, just to kind of see what happens. This is an example of one that's not in the indeterminate form yet. Like as x approaches infinity, this thing is like, I don't know, e to the x squared as x approaches infinity is infinite, and e to the negative 3x is 0. So this is like, I guess like this one, but there's a bunch of different indeterminate forms that can be written as L'Hopital's rule, and this is one of them. You could write this one like this. Let's remember that e to the negative 3x is equal to 1 over e to the 3x. So this is really the limit as x approaches infinity of x squared over e to the 3x. E to the 3x goes to the bottom because the exponent's negative, and now this as x approaches infinity is infinity over infinity. As x gets very large, this gets very large, and this gets very large. So this is now an infinity over infinity indeterminate form, and we can use L'Hopital's rule. So our first run at it, limit stays the same. And we take the derivative of the top, which is 2x. The derivative of the bottom, which is e to the 3x times 3, because of the chain rule. I'm going to write that as 3e to the 3x. And now I look again and I'm like, can I plug in infinity, so to speak? Can I let x get very large? And does anything interesting happen? And the answer is, I'm going to write x equals infinity. Of course, x never equals infinity because that's not a real thing. But as that happens, you get 2 times infinity, which is infinity, and 3 times e to the infinity, which is infinity again. So this is another indeterminate form. And I can use L'Hopital's rule a second time. That's kind of the point of this problem, to show that you can use it twice. So I'm going to use it again. I'm going to use L'Hopital's rule now on this fraction. The derivative of the top of this fraction is 2. And like before, that tells me that this is the last time I'm going to use L'Hopital's rule, because this is no longer, again, it's not going to be 0 over 0 or infinity over infinity this time. The bottom here is 3 times the derivative of that, which is 3e to 3x. So I get 9e to the 3x here on the bottom. And now as x approaches infinity, the top is just 2, and the bottom is infinity, and 2 over infinity is 0. So this original limit, we did L'Hopital's rule on it twice. Derivative of the top and the bottom, derivative of the top and the bottom. Eventually the top stopped being infinity and became 2, and the bottom remained infinity the whole time. So we got 2 over infinity, which is 0. So that's like a demonstration of how L'Hopital's rule can be used more than once if necessary. In this case, we got a nice answer of 0. Sometimes you might end up with like infinity over 2, which would be infinite, and that would be like it does not exist or an infinite limit. What other examples do we got? We might skip this one and maybe do it in class or something, but this one doesn't look like anything really. Like if I look at this and I try and plug in 0, I'm like, as x approaches 0 from the right, x itself approaches 0. As x approaches 0 from the right, you might want to think about what the natural log of x, the graph, looks like. It looks like this. This is y equals natural log of x. So as x approaches as x approaches 0 from the right, go to the right towards 0, this thing approaches negative infinity. So this ends up being like 0 times negative infinity, which is an indeterminate form of this sort. It's like 0 times an infinite quantity, which is not something I can assess. So the way to rewrite these, maybe the smart way to rewrite this is to rewrite it like this. You can rewrite this as the limit as x approaches 0 from the right of log x over 1 over x. And just to confirm for you maybe that this log x over 1 over x is the same as the thing we started with. Like when I divide fractions, which is basically what I'm doing here, I multiply the top by the reciprocal of the bottom. So it'd be like log x over 1 over x is log x times x over 1, which is x times natural log of x, which is where I started. So I can rewrite it this way, just so I can get a fraction, because L'Hopital's rule works on fractions. And this is not a fraction, but this is. And now if I look, as x approaches 0 from the right, log of x approaches infinity, negative infinity technically, and 1 over x also approaches infinity. In this case, 1 over x from the right approaches positive infinity, but it doesn't really matter. Infinity over infinity, infinity over negative infinity is the same thing. So this is now like basically it's negative infinity over infinity, which is indeterminate. So I can use L'Hopital's rule. So L'Hopital claims that this limit is equal to this limit. The derivative of the top is 1 over x. The derivative of the bottom is negative 1 over x squared. You could think about this bottom here as being x to the negative 1. Derivative of that is negative x to the negative 2, which is negative 1 over x squared. And now I can simplify this fraction a bit. I can multiply the top by the reciprocal of the bottom, 1 over x times negative x squared over 1, which is, I can move the negative to the outside if I want to, negative limit as x approaches 0 from the right. And x squared over x is just x. So this is negative limit as x approaches 0 of x. The limit as x approaches 0 from the right of x is 0. So this equals 0. Negative 0, which is the same as 0. So this limit equals 0. The point here was to demonstrate to you that you can pretty much always write any product, like x times the natural log of x, as a quotient. And then use L'Hopital's rule on that if possible. In this case, once I rewrote it as a quotient, I ended up with an indeterminate form, so I could then use L'Hopital's rule. And I did that to the derivative of the top and the bottom. And then I simplified what I got, and it ended up being something I could just plug the 0 in and get an answer. So, and like I said, we'll skip this one. We'll come back to it maybe in class or something. I think this one ends up being 0 over 0, but we'll talk about that later. This is one that came actually from an AP test. The limit as x approaches e of this ridiculous thing on top here, this ridiculous fraction. And so our first goal, our first job is to plug in e everywhere we see an x and see if we get 0 over 0 or infinity over infinity, and thus we could take the limit. So I'm going to plug in e everywhere I see an x and see what happens. I'm going to let x equal e. Remember, e is a constant. So this becomes e to the 20th minus 3e minus e to the 20th. Then minus 3e is plus 3e. The bottom is, when x is e, this is just e minus e. So the bottom is pretty clearly equal to 0. On top, I got 1e to the 20th here, and then a minus e to the 20th there. And I got a minus 3e here and a plus 3e there. So I get 0 over 0, which is an indeterminate form, which means I can use L'Hopital's rule. So this limit, according to L'Hopital, is equal to the limit as x approaches e of, see, the derivative of x to the 20th is 20x to the 19th. The derivative of negative 3x is negative 3. This whole thing here is just a number. It's like a weird number, e to the 20th minus 3e, but it's still a constant, which means this derivative is 0. Derivative of the top is just 0. Sorry, the derivative of this part is just 0. In the bottom, I get 1 minus 0, so that's 1. And this tells me right away, that 1 there, that I'm done with L'Hopital's rule, because the bottom is no longer either 0 or infinity. Plug in x equals e, and I get 20e to the 19th. minus 3 over 1, which is just this. And so the answer is B. So that's a way to use L'Hopital's rule for this multiple choice question. Again, check and make sure that it's an indeterminate form. If it is, derivative of the top, derivative of the bottom, and then try and reevaluate it. And again, if this had been another indeterminate form here, I could just use L'Hopital's rule again. So that's how you use L'Hopital's rule. And I'll see you guys in class. Bye.